My name is Grace Drew, and this is my Physics 2 Lab 5 magnetic molasses. So the overall purpose of this lab was to apply Faraday's law by observing a magnet falling down a conductive aluminum foil tube. A computational model of the magnet falling through the tube was curated, and the predictions that the computational model spit out is compared to the observed data. The experimentally observed amount of time was 1.58 seconds, and the experimentally observed amount of time was 1.464 seconds. The assumptions for this experiment include that the bar magnet was acting as a magnetic dipole, air resistance was negligible, and the only forces acting on the magnet were gravity and magnetism. The physical principles we used for this lab were Faraday's law, the Biot-Savart law, Ohm's law, which is current equals voltage over resistance, Newton's second law, which is force equals mass times acceleration, magnetic force, and the time derivative of magnetic flux. So for this experiment, we had the system, which was a magnet and aluminum foil, and then the surroundings, which was everything else around the system. So in order to curate the experimental amount of time it took the magnet to fall, we found the north end of the magnet using the magnetometer app and dropped the magnet down the tube of foil north side down, and we filmed this. We repeated this process 5 times, so we had 5 videos of the magnet falling down the aluminum foil tube. We then recorded the amount of time it took for the magnet to fall in each of those 5 videos and averaged together to get 1.58 seconds. Now it was time to curate the computational model. So step 1 of the code was to edit the properties of the magnet. So the mass of our magnet was 0.025 grams, and the magnitude of the magnetic dipole moment, which we took from lab 3, was 1.158. Next, we had to create a function to calculate the magnetic field of bar magnet using our lab 3 code. So this, the definition of the dipole B, was imported from lab 3, where we had the magnitude of R hat, and then B, the function of B. And then step 3, we had to create a function to calculate magnetic flux. Here you can see that we just edited the numerator and the denominator using the derivative of magnetic flux. Step 7 was to calculate the gravitational force on the magnet. So here you can see we computed the d flux dt for the ring via the falling magnet, and then found the current of the ring using that d flux dt. Next, we computed the typical B field at each ring, and that is seen under steps 5 and 6. And then we calculated the net force on the magnet, which was F gravitational plus F magnetic. Lastly, we updated the magnet's velocity and position in order to curate the graph by applying Newton's second law. And then last, we were able to curate the plot. So to the right, you can see the actual plot of the magnet falling in velocity versus time. And this spat out a time of 1.464 seconds. At the top, you can see a blue section of the tube at the bottom. And this was the color at the very end of our computational model, but during it had a fluctuating color between red and blue. So that color on the tube indicated the direction of the current flowing. Red was counterclockwise and blue was the clockwise flow. And then the graph shows that at the beginning, that initial sharp decrease, the magnetic and gravitational forces were unbalanced. When the graph leveled out, the forces equalized, and then at the very end, the forces unequalized again. The experimental time we calculated initially was 1.580 seconds, and the computed time was 1.464 seconds. So that left us with a percent error of 7.34%. This could be due to several sources of error listed below. Lastly, our what-if question was if the resistivity of the conductor was reduced as close as possible to 0, how would the dynamics of the falling magnet change? And there would be a larger induced current, meaning more magnetic force felt by the magnet, and the magnet will fall slower through the tube. What if the